The next learning objective is I can recognize forces acting on objects in a system and determine if conservation of momentum is valid. Now this is the start of our talk about conservation of momentum, which is probably the most important concept in all of physics. This learning objective is going to be a more conceptual approach to conservation of momentum. We're not going to be doing too much math. We're just going to be looking at the concept of conservation of momentum and checking whether we could apply it to a problem. Technically, the conservation of momentum is always valid. It's a fundamental truth that has yet to ever be disproved. But some problems, it's not going to be helpful for us to apply the conservation of momentum. Some systems are not set up such that conservation of momentum would give us any kind of meaningful results. This would be like trying to apply the quadratic equation to a straight line. The quadratic equation is always true. It's just not useful unless you're dealing with a quadratic. All right, let's define what the law of conservation of momentum is saying. So, what the law of conservation of momentum is saying is that the total momentum of a closed system, and that is an important concept right here, this idea of a closed system. The idea behind a closed system is that you're not going to have matter going into or out of the system. So all the objects that are in your system to start with are going to be all the objects in your system afterwards. You can't have a starting system that has 3 objects and then an ending system that only has 2 objects. Like, you can't lose mass or gain mass while in the time frame that you're considering. So a closed system, in a closed system, the total momentum remains constant, so that means it does not change, so long as there are no external forces. You can have internal forces, but you can't have any external forces. Mathematically, what this is saying is that the sum of all momentums initially, so that's what this is, the sigma there represents the sum of all momentums initially equals the sum of all momentums final. So if you add up all the momentums initially and you get, let's say, 5 kilograms times meter per second, then if you let time go on, maybe you let 5 seconds elapse and then you measure all the momenta later, you'll find that it will still be 5 kilograms times meter per second. Let's take a look at an example. Let's say we have a 2 kilogram object going to the right at 3 meters per second. And we have another object that is also 2 kilograms, and its velocity is 0. Overall, the total momentum before is going to be equal to the momentum of the first object, which is 2 kilograms times its 3 meters per second, plus 0, because the other object has no velocity, so its momentum has to be 0. That's going to give us a total momentum of 6 kilogram meter per second. Let's let time elapse. These two objects are going to collide, and the first object is now at rest, and the second object is now going 3 meters per second. And we would know that this second object must be going 3 meters a second, because if we add up all the momenta afterwards, we're going to get, well, first off, for the first object, we're going to get 0, because now it is at rest. And then we're going to get, for the second object, 2 kilograms times 3 meters per second. That's going to get us a total momentum at a later point in time of 6 kilograms times meter per second. And what we can see here is that the sum of all momenta initially equals the sum of all momenta final. That's what Newton's second law. That's what the conservation of momentum is saying. Let's take a look at a case where conservation of momentum is not valid to apply. So this is where conservation of momentum would not help us solve for any of the variables in this physics problem. Here's the situation. We got two objects, and they're both on a ramp. One object is going up the ramp at 3 meters a second. Another object is going down the ramp at 2 meters a second. And this ramp is on Earth. So both of these objects are going to be experiencing a force of gravity. So we can draw that in there, free body style. Both of these objects are going to be experiencing a force downwards of gravity. And they both have the same mass of m. The specific number for the mass here isn't going to matter at all. So we're just going to put m, both the same mass. If you look at this physics problem and completely ignore the existence of the second object, so you just have one object going up the hill, we can already tell that this object's momentum is not going to remain the same. This object is going to go up the hill, eventually stop, and then loop back and start going down the hill. It is not only going slower after a while going up the hill, but eventually it's going to switch directions, which ultimately does change the momentum because it's changing the velocity. Remember, any direction change of velocity is also a change in velocity. And the same thing is going to be happening to the second object, except it's not going to change direction, so go slower. It's just going to continually picking up speed. Overall, this entire system is going to be gaining speed in the downwards direction. So we can tell right now that the momentum we're going to get initially for the entire system is not going to be the same as the momentum we get later. So here's a later point in time. Both objects are going down the hill. If you quickly look right here on the first scenario, we had, if they have the same mass and this object is going faster, the net momentum is going to be going up the hill slightly. But now, since both objects are going down the hill, the net momentum is going down. So the reason that this does not apply, the conservation of momentum does not apply, is because we have an outside force of gravity. We're not taking into account gravity into this scenario. Gravity is going to change both of the masses' momenta. And therefore the sum of momenta before cannot equal the sum of momenta after. Let's take a look at another example when the sum of momenta initial does not equal the sum of momenta later. So let's say we have a car. The car is originally moving at 30 meters per second. This car is going along, it's moving at 30 meters a second, and eventually it hits a wall. The car comes to a stop. Might crush a little bit, but ultimately the car does come to a stop. Why does it seem like the law of conservation of momentum is not valid in this situation? Well, we can see that the sum of momenta initially is greater than 0. Well, I guess absolutely. Well, I guess technically the absolute value of a sum of momenta initially is greater than 0. It's just not equal to 0. But then we let this progress, it hits the wall, and stops, and then we have the sum of momenta final does equal 0. So it looks like the sum of momenta initially does not equal the sum of momenta final. That's what this looks like. But we're not taking into account something. When this object, when this car hits the wall is going to push back on the car. And this force, the force of the wall on car, is an outside force, an external force, that is not being taken into account here. Also, we could think of it this way. This car is applying, this car is going to be transferring some of its momenta. This car is going to be applying, this car is going to be transferring some of its momentum into the wall. It's going to be pushing on the wall. And our system isn't including the wall. So the force that the wall pushes back on the car comes from outside the system we're considering. The conservation of momentum would be valid to apply here if we also included the wall. The problem with including the wall is, what's keeping the wall here? What's keeping the wall from moving? Well, it's bolted to the ground. So ultimately, the wall is also going to have an external force from the ground to keep it there. Okay, well, let's just include the ground. That basically means that we have to include the entire Earth below it. But if we did include the entire Earth below it as part of our system, then the conservation momentum would be valid. We just have to include how the velocity of the Earth changes because of this one car collision, which is not going to be a very large number. We do not change the velocity of the Earth very much by hitting a car against a wall. Let's look at a scenario where the conservation of momentum is valid to apply and explain why that would be the case. So for this example, we're going to have two astronauts are floating in space outside their spaceship. They push off each other and drift in opposite directions. So can the conservation of momentum be applied in this situation? Then we're going to explain our reasoning by considering the system of the two astronauts before and after the push, and whether there are external forces acting on them. Let's look at before and actually during the push. So this is before/during the push. So the push has just started. The sum of momentum equals 0. The entire system's momentum is 0. And by the way, this right here is our system. Everything inside the box is considered to be inside our system. So each of these astronauts are pushing on each other. So the right astronaut is applying a force, which I've represented right here, on the left astronaut. And the left astronaut is applying a force on the right astronaut. What's key is that the force acting on the right astronaut, the source of that force is coming from a push from an object inside the system. This would be considered an internal force. The same thing applies for the force that the left astronaut is feeling from the right astronaut. The right astronaut is inside the system as well, and it is applying the force on the left astronaut. So both of these forces are internal in the system. They both come from objects also in the system and also being taken into account. Before the push, the sum of all momenta is 0 because we're considering them to be not moving at this time. After the push, though, the astronaut on the left-hand side has gained negative momentum because we're going to consider that to the left is negative, like convention. The right astronaut has gained positive momentum. And we're going to go ahead and assume that they weigh the same, they have the same mass. And when this happens, when they push on each other, since they apply it with the same force to each other, and over the same length of time, they're going to pick up the same velocity, just in opposite directions. So if we add the rightwards momentum of the right astronaut and the leftwards momentum of the left astronaut, we're going to get two numbers that equal each other, but there's a negative sign in between, so we're going to get 0. Here are two practice problems to practice applying. Here are two practice problems. Both are asking you essentially the same question. Can you use the conservation of momentum? Is it valid in this situation? And then to explain the reasoning by looking at the forces, whether there's external forces or just internal forces. The first problem has a child standing on a skateboard at rest on a smooth, level surface. They throw a heavy ball forward. So can you apply the conservation of momentum to the system? And then explain by talking about whether there are external or internal forces. The second problem, A car collides with a stationary truck on a frictionless, icy road. After the collision, both vehicles move together. Is the conservation of momentum valid in this scenario? And again, explain why using a look at the and again, explain why by looking at the forces, both internal and external.